Hello, this is Mr. White, and this video is on Ugly Algebra Part 2, this time including radicals, which will make our job slightly more challenging, but nothing we can't handle. Once again, our objectives are to continue introducing the concept of the derivative, which is a major topic in calculus, and to become fluent with the algebra that comes up often when working with derivatives in calculus. So let's get to it. Here's our example, and same instructions as in the last video. We're going to for a given function, which could either be an unnamed function, y equals, or a named function, such as h of x equals. For that function, we're going to fully simplify its given derivative. Again, y prime or h prime for a named function. We're going to find the critical numbers and or vertical asymptotes and check all of this out on a graphing calculator, intelligently choosing the window settings. So, as I did in the last video, rather than deal with the product that you see on the screen right now, I'm going to make things just slightly messier by dealing with the quotient here. So let's make that our example function, h of x. And again, the thinking is that if we can handle the quotients, then the products should be manageable as well. So let's replace that derivative with its updated derivative, the quotient version, and ask you to ponder, what do you think is the first thing we're going to do to neaten up that algebra? By the way, I'll point out here, if it's not already obvious, that when you're in calculus class, you'll be tasked with coming up with this derivative expression on your own, but for as long as we're in pre-calculus, I'll supply the derivative expression, and your task will be just to neaten it up with algebra. So, what do you think our first step should be? Well, in our last video, the first step was to take out a greatest common factor, and that is possible, and if you're feeling adventurous, I'd encourage you to try it, but over the years I've found that students often have trouble pulling that off correctly. In particular, this negative exponent up here tends to cause a lot of trouble when students start factoring. So again, try it if you're feeling adventurous, but I'm going to recommend another approach. Speaking of that negative exponent, I'm going to recommend we reveal it as the fraction in disguise that it is. Isn't that what a negative exponent means? Doesn't it mean that that factor really belongs in the denominator with a positive exponent? So let's write this entire term as the fraction that it is. Let's take the 20 times 1 over 6, that gives us 20 over 6, but let's go ahead and reduce that to 10 over 3. This factor, 5x plus 4, has a positive exponent, so let's keep that in the numerator, 5x plus 4 with an exponent of positive 11. And this factor here with the negative exponent, let's go ahead and put it in the denominator as 20x minus 7 to the positive 5/6 power. So whether or not you like fractions, we have to recognize that we are dealing with them here, and we have uncovered this fraction in disguise. Let's turn our attention to the first term up there in the numerator. I'll simplify it slightly. 5 times 11 gives us 55. I'm going to write this factor next. 5x plus 4 to the 10th, followed by this one. It's all multiplication here, so the order in which you multiply these is not crucial, although I have my preferences, and you'll probably develop your own preferences as well. And all of that is over this denominator of 20x minus 7 to the 1/3 power. Oops, there's an x in there. Now, why do you think I left all that space up there in the numerator? What do you think? Oh, by the way, this is being subtracted, right? And that's actually kind of hints at why I left that space there. When we subtract a fraction minus another fraction, or even a non-fraction minus a fraction, what do we typically do? We do common denominators, don't we? So let's create a common denominator. Right now, this first term up here in the numerator has a denominator of an implied 1. But I want it to have this as its denominator. So let's go ahead and put that as its denominator. 3 times 20x minus 7 to the 5/6 power. And I'll put it up there in the numerator as well. That is our fancy one. You can multiply any expression by fancy 1 in the form of some non-zero expression over itself. You just multiply by 1. You can always multiply by 1 without changing the value of an expression, right? All right, so what next? Well, let's start neatening up that numerator. And by numerator, I'm referring to all of this. And now that it has a common denominator, we can put it over this common denominator of 3 times 20x minus 7 to the 5/6. Again, that's the denominator. Let me focus on this term's numerator first. 55 times 3 will give us 165. 5x plus 4 to the 10th. And something nice happens here, you may have noticed with the exponents. 20x minus 7 to the 1/6 times 20x minus 7 to the 5/6. When you add those exponents, 1/6 plus 5/6 just gives us 6/6, or 1. So 20x minus 7 to the 1 power is what that becomes. Now I'll subtract this numerator, again, all over that same denominator of 3 times 20x minus 7 to the 5/6. And as far as this denominator underneath all of that, if I wanted to keep putting all of that over that denominator, I could, but let me go ahead and start handling that in this step right here. Let's go ahead and multiply by the reciprocal of that. And the way I'm conceptualizing it, I'm thinking of that as a fraction in its own right, 20x minus 7 to the 1/3 over 1, and when we divide by that fraction, we multiply by its reciprocal. If you conceptualize it in some other way that leads us to the same place, I'm fine with it. All right, what next? Well, I'm going to go ahead and start by addressing that denominator first. You could tackle the numerator first if you want. I'm just choosing to look at the denominator and notice that 3 times 20x minus 7 to the 5/6. Well, oops, didn't mean to write that. Because when you multiply 20x minus 7 to the 5/6 times 20x minus 7 to the 1/3, we add their exponents, right? So 5/6 plus 2/6, I'll call that. 5/6 plus 2/6, that's 7/6, right? And as far as the numerator, what could we do with the numerator? Well, think back to that first step in the last video, when our first step was to take out a greatest common factor. And this is the point where I would claim that's our best move. Like I said earlier, you could have factored earlier when we had negative exponents, but I think this is the better time to factor now that all those exponents are positive. So what is the greatest common factor between those two terms in the numerator? Well, 165 and 10 are both divisible by 5, so that's going to be part of our greatest common factor. And I see a 5x plus 4 to the 10th and a 5x plus 4 to the 11th here. So that means that 5x plus 4 to the 10th is part of our greatest common factor. I'll put some big parentheses here. And what goes inside the big bold parentheses? Well, 5 times what will give us 165? 5 times 33 will produce that 165. We've already taken out all of that 5x plus 4 to the 10th in the greatest common factor, but this is still left inside, right? So 20x minus 7 minus, in the second term, again, we took a 5 out in the greatest common factor, so that leaves us 2 here. And then 5x plus 4 to the 10th was taken out, so there's a single 5x plus 4 left on the inside, in parentheses. For our next step, I'm just going to simplify what's inside those big parentheses. So let's distribute. 33 times the 20x minus 7 will give us 660x minus 231. I highly, highly encourage you to practice your mental math throughout this process, but I also acknowledge that at some point these numbers are getting big enough where I'm not totally mad at you if you use a calculator on some of these larger numbers, but do try to practice the mental math as much as you can. And also make sure you notice that this is going to be minus 8 at the end. You're familiar with this stamp, perhaps, and the crime that it represents. Make sure you correctly distribute that negative sign and have a minus 8 at the end there. All right, so if you're hanging pretty well so far, good news is we're getting near the end. I'm just going to take another small step here and combine the like terms inside the big bold parentheses. So 660x minus 10x is going to give us 650x. And then minus 231 and minus 8 is going to give us minus 239. And as I mentioned in the last video, we may have our fully simplified derivative right here. The only thing I want to check for is to see whether there's a greatest common factor in 650x minus 239, a factor greater than 1. So my little cheat, my little shortcut for that was to go to the calculator and put 239 divided by 650 On a TI calculator, math enter enter will give me the fraction in fully reduced form. And the fact that I still have my original 239 over 650, the fact that that hasn't been reduced tells me that there is not a common factor between them. So the good news is we are done fully simplifying this derivative. I'm going to go ahead and, as a formality, just reiterate, just emphasize that this was h prime of x. And in order to find the critical numbers and our vertical asymptotes, we'll set that equal to 0 or undefined. And again, I'm leaving that mostly to classroom discussion to get into why we're doing that. I hope that makes sense to you as you watch this, but even if it doesn't completely make sense, the algebra hopefully is going your way. So let's see, to make the derivative equal to 0, that means the numerator must be 0. So if I set that factor in the numerator equal to 0, I'm going to get x equals negative 4 over 5. If I set this factor in the numerator equal to 0, that's going to give me x equals 239 over 650. And to make the derivative undefined, that means the denominator must be 0. So if I set that factor in the denominator to 0, I get x equals 720. And as mentioned in the last video, we should recognize from earlier pre-calculus skills that that is probably our vertical asymptote, right? Not just in the derivative, but in the original function, the original h of x. So let's go to the calculator and type in the original h of x, not this derivative. There is the original function, and if I kind of reset my window settings to zoom decimal or zoom's standard, I'll go to zoom decimal, I don't see anything. That's not completely unexpected. Remember, we're going to trace to those critical numbers to get a sense of where this graph is. I'm going to trace to the ugliest one, the messiest one first. Let's trace to that 239 divided by 650. And look at that large y value. It looks like a 3 followed by 8 more digits. So we need to set a y max that gets us up in that area. So I'm going to set my y max to, let's say, a 7 followed by 8 zeros. Let's do that. So I'll do 7 followed by 8 zeros. And I like to set the y min to something comparable, something in the ballpark of that. So I'll do negative 1 followed by 8 zeros. And, well, I see something. It's still not a great picture here, but what I might notice next is all the wasted space in the left and right side of this graph. And notice that let me very quickly go back to our critical numbers. Notice that these are all fairly small numbers. They're all between negative 1 and 1. So if those are the numbers, the x values we're interested in, let's set our x min to negative 1 and our x max to 1. Looks a little better. From our previous calculator experience, we may still have some sense that something's not quite right here. Let's see, let me trace to one of the other critical numbers. Let me trace that negative 4/5. Somewhat switching gears here. And when I do that, notice there's no y value at all. And when you think about it, we can find that that's actually an extraneous solution. If I bring back the original function even, and if you imagine plugging in that negative 4/5 into the original function, you see how that's going to create a negative number underneath this even indexed root? 20 times negative 4/5 minus 7 is going to be negative. And if I try to take the 6th root of that, we get undefined. We're not dealing with complex numbers here, right? So that tells me that I'm not really concerned about that one. Let me go ahead and cross that out and say extraneous. I do still think that 7 over 20 is a vertical asymptote. So to investigate that a little bit, I'll trace to 7 over 20 and verify that I'm not getting any output at all. I'm not getting a y value. But if I trace to 7 over 20 plus just a little bit, I notice that I do have a y value, and it even shows that there's a y value there on the graph that wasn't originally visible due to just limitations of our calculator. So if I really feel the need to get a closer look at what's going on there, let's set a really narrow x min and x max. Let's see, that 239 divided by 650, what was that as a decimal? 0.367. Our asymptote was at 0.35. That's the 7 over 20. So how about let's just go ahead and make the x min right at the asymptote, 7/20ths or 0.35. And let's just go over to 0.5. Let's have a really narrow window there. And now I'm getting a much better look. This is taking some intelligence, this is taking some thought to get this to appear cleanly on our calculator, but hopefully you feel like there's some payoff here when we trace to 239 over 650. And voila, there it lands at what appears to be the minimum of this graph. That seems to support that we've done everything correctly algebraically. All right, that was a lot. If that all made sense, kudos to you for hanging with this. Let me kind of summarize here. Again, there's our vertical asymptote, our local minimum. The other thing that we thought was a critical number at -4/5 turned out to be extraneous. Those are the window settings that I chose, or they appear that way, right? So with a little bit of keeping our brains engaged using the calculator, we're able to get some good results there. Hope that all made sense. Time for you to put your skills to work here. All right, there's your function, j of x, same instructions. There's the given j prime of x derivative. Go ahead and pause the video at this time and see how you do. Okay, I'm going to assume you've already given this your best shot and hopefully come up with some good results. Just for the record, let's compare. First things first, write your fraction in disguise as the fraction that it is, and that empty space was for the common denominator, the fancy one, right? From there, we simplify all the stuff in the numerator, and then as far as that 8x plus 3 to the 2/7 on the bottom, we go ahead and multiply by its reciprocal. Next step is where I recommend that we wait till this point to factor, and our GCF, our greatest common factor in this case, was 4 times 5x minus 11 to the 11th. Compare against all the stuff inside the bold parentheses there. Next step is to start distributing the stuff inside the bold parentheses, again making sure that you distribute that negative sign correctly. From there, we deduce that 337 and 830 do not have any common factors, so we can call this our fully simplified derivative. We set that equal to 0 or undefined. That gives us these three critical numbers. I'll call them loosely. Again, at a later time, we'll discuss whether all three truly are deserving of being called critical numbers or not. But for the time being, I'm just going to roll with it there. And on a calculator, you investigate a little bit, and using keeping your brain engaged, you come up with some window settings that allow you to find that local maximum, that asymptote, and that local minimum. Notice that there were no extraneous solutions this time. Just real quickly, that was because the radical in the original function had an odd index. It was an odd radical, odd index radical instead of an even index radical. And reminder, how did I come up with those window settings? When you trace to this critical number and you see this y value, that E13 tells us that we have a really large negative number. As our, so that's why I set the y min to -4 followed by 13 zeros, and set the y max to something comparable. Those window settings, along with a very narrow x min and x max, gave me a good glimpse at this local maximum. To get a better glimpse at the other critical number, which again, this time was not extraneous, I found that these window settings did a fine job of convincing me that I'd found a local minimum. Okay, hopefully you're getting the hang of all this, and thank you for watching. I'll see you in class.